All right, so we are now recording. Hopefully you had a chance to watch the lectures. I made a little mistake. Thank you, Chad, for pointing out. I uploaded the lecture, but I forgot to link them all to the Canvas page. So lecture A was there, but B and C, I neglected to put the links up. So they should be there now. I just put them up a little over an hour ago. So I'm sorry if you're looking for the lectures and couldn't find them. They were there on the YouTube page. They just didn't have the links. So just remember there's the YouTube page and then the Canvas linking to the YouTube. So if it's not on Canvas, it's probably on the YouTube. But we will be doing, we're getting into, I guess, the real meat of microwave engineering is the matching networks, at least for this class. This is kind of really what we've been building up to for the last couple months is these matching networks here. So all that background on transmission lines and Smith charts. Then we took a big detour with waveguides, which is important stuff, but now we're coming back again to this network analysis stuff. And we're gonna do pretty much just matching and transmissions through things for the next few weeks, all the way to the end of the class. So if you look onto the Canvas page, there should be a quiz up. Let me go see if I can find it. So we got a nice practice problem here, where we're going to walk through it very slowly because there's a lot of things about the book that sort of irk me in the way it approaches this matching stuff. It just kind of assumed you know certain things that weren't really emphasized. So I kind of feel embarrassed now for talking up POSAR earlier this semester. Like, it is a good book. There's lots of good information, but just some of the way the material is approached, I would have done it a little differently. Because like with the lumped element matching, it just sort of jumps in and just says, here, let's match things using lumped elements. And the intuition between the algebra and the Smith chart is not made super clear in the book. And especially the notion of impedance versus the admittance transformation. I mean, I looked back through chapter 2 and it's all just Smith chart, impedance, and there's like one little subsection where it says, oh, by the way, you can do an admittance thing here. And it's just kind of assuming you know certain little subtle details. So what I'd like to do is, we've got a problem on Canvas, so let me do my screen share here. So this is a classic, lumped element matching problem. We got a 50 ohm transmission line, and there's a load impedance of fill in the blank, 100 plus 75J, right? So I just pick some random values here, and we'll tweak with those values a little bit as we go through. And it's just design a lumped element L section matching network, and then repeat for a slightly different load, because you have to do slightly different rules depending on what the load is. And then calculate capacitance or inductance for some center frequency. We'll do that. And then try and do the frequency response. And this is another little thing I thought was kind of, I guess, adorable about the textbook. So here, let me find this section here, where it plots this frequency response here. And it gives you a complex look. So sorry, let me go back to the overhead camera here. So I'll stop sharing. I'm going to pin this. So they give you, some complex impedance here, 200 minus 100J ohms, right? And they do the L section match, and they're like, hey, let's plot the frequency response of that. And like that's good from a sort of pedagogical perspective. But I remember just kind of chuckling, like, oh, how adorable. He thinks the load impedance won't change with frequency as well. So it's a good exercise to do it. But one of my little questions is, do you really think there will be a load in practice that is going to be constant over frequency? Like a classic example would be something like an antenna, where that impedance will not be a constant value. It will change at every frequency you excite it at. So this sort of graph is, I guess, interesting to kind of go through the exercise, but in practice, this load will also change. You'll only really know this at one particular frequency. And then as you go off frequency, it will change, which means your matching properties are going to change with it. And so you'll never quite get such a clean frequency response out of that. So we'll go back to screen share. So that's that last question. Is it reasonable to assume your load really is going to remain constant at all your frequencies? Maybe there are some devices that do that, but I would say definitely with something like an antenna, that's not going to be the most reasonable assumption anyway. So we're going to kind of go through that and talk about that step by step. So first things first, let's just start. So I put together the script here. Oop, this should say Friday, October 30th. There we go. And we'll just we'll just go through this thing step by step. And I really want to focus on that perspective of the Smith chart. Because this is, I think, something the book does well. At first, it does sort of the analytic approach. Let's just do this from the pure algebraic perspective, where it matches the real and the imaginary bits, and you get some nice closed form equations. And then they do it from the Smith chart perspective. And in this case, there's a lot of value in thinking about this stuff in terms of the Smith chart, because you have to make certain design decisions along the way. And the Smith chart is a very powerful tool to just visualize where you are in that solution space. So, Corey made the comment a long time ago that the Smith chart is kind of like an analog computer, and that is very, very true. But sometimes in this context, it just helps to think about these matching problems in terms of the Smith chart as a visual aid that follows very simple geometric rules that are totally in contrast from the actual algebraic expression. So I want to kind of do this parallel approach where we'll just sort of do the math, but then we're going to visualize each step along the way using sort of like a Smith chart plot, okay? So let's go ahead and get into that. Define our model parameters. So you notice I kind of already did this. I'm just going to walk through sort of step by step as we go. So what do we have? 50 ohm line with 100 plus J75. So we'll say Z naught is 50. Feel free to follow along as best as you can, but I will upload this when it's done, because this is going to be a very kind of useful script to have in terms of visualizing this stuff and playing with it later. 100 plus J times 75. Actually, you can just say 75J when you're using MATLAB. Load impedance. You notice it's complex. That's very, very important. And in fact, just for the sake of argument, I was going to say, let's do a very simple case sort of for ZL is equal to 50, or say Z naught plus 75. So I'm going to do a simple case first where the real part matches the characteristic impedance, and then we'll kind of step away from that after we've explored that for a little bit. So we'll do sort of a test case. There you go. And let's see, so we had a center frequency of 500 megahertz. So also, I have another little note here. So ZL was going to be 25 plus 75J. This is going to be our second case. So I'll just comment that out, right? So we'll uncomment that when we're ready to get to it and just leave that there. And we're going to explore this case real quick. And then, of course, F naught is 500 megahertz. We'll call it the center frequency. So that's the desired matching frequency there. So first things first, let's just do, I'm going to copy and paste a little bit here. These guys here. So first, you calculate the normalized load impedance, Z sub L. So this will be a nice comparison with the Smith chart here. And then we're going to calculate the reflection coefficient, for sort of the default gamma. And then we'll draw the Smith chart. So remember, we created this fun little script or function called create Smith chart. So we won't even draw anything on. I'm just going to run this as it is. So you notice this script will create kind of this nice little digital script, our Smith chart here, which Jackie wrote most of this, and then I kind of polished it up. So this is actually going to be a very slick little tool for visualizing some of this stuff. So here is a blank Smith chart, and then we have our default reflection coefficient. So remember, the Smith chart is just a polar plot of the reflection coefficient lying within that unit circle. So I'm just going to plot real, imaginary, and I'm going to make a big giant black dot out of it, right? So there you see it there. So the key for this example is, because the real part of that load matched the characteristic impedance, you notice it landed on this circle here. The I guess R equals 1, or the real part of our normalized impedance is 1. So that's a very, very important point, because it just means if I have to add or subtract the appropriate reactance, it will follow that circle in one way or the other. And so and intuitively, you can see that in terms of the real part is matched. I just have this reactance I need to get rid of, right? So if this was, say, an inductor, I would put a capacitor in series, which would have a negative reactance, and it would cancel out that bit to give me just a real value, right? So let's do a quick little visualization of that. I'm gonna go back to my pencil and paper here. So we'll stop sharing. So I'm looking at the overhead camera here. So a very, very simple case might look something like this. So here's my load. And just for kicks and giggles, suppose it's a resistor plus some inductor like this. So this is sort of like the equivalent circuit, right? So this was 50 ohms, and this guy here, whatever the inductance is, it has a reactance of J75. So all I have to do intuitively is say, if I just put, say, a capacitor in series here with the appropriate value, it will negate this reactance over here, right? So you would just say my Z in is going to be the capacitance plus the resistance plus this inductance here, which will just be capacitance plus 50 ohms plus J75. So you notice I'm doing this in kind of in abstract, so that's a 7, kind of just abstract terms, right? Because in order for a specific inductance, I would have to have a frequency. So you take that product together and we get some net impedance, right? And then we know that ZC is going to be negative J over omega C. And I'm going to write this as the following: negative J over omega C plus 50 ohms and plus J75 ohms here. Or more generally, you can think of it as RL plus JX sub L. So there's the real component to the load and then the reactive component. And I just want this to equal the negation of that. So so all I have to say is negative J over omega to C is equal to negative JXL. So I want these two terms to cancel out. And so you solve for C and you get something like C equals 1 over omega XL. That should make sense, right? Because a series combination of a capacitor and an inductor at the right resonant frequency, these two reactances basically annihilate each other, and I'm just left with my 50 ohms. So this is sort of the intuition of how a lumped element should work. So I'm going to call that ZL, and I'm going to call this JX. So not to be
we have a
yeah.
We have a question about why you chose series instead of parallel to drop that cap in.
Oh, because when it's series, you just add them up linearly over here. When it's parallel, the rules will be slightly different. So we can kind of do a parallel case next. This is just sort of an example to show you what the lumped element matching is kind of doing. And I want to be able to visualize this in the Smith chart first. So this is just to keep it simple first, and we'll build complexity as we go. So the reality, though, is it may not be a resistor and inductor. This is just going to be a black box with some net impedance, and it happened to have a positive reactance to it. Therefore, I needed a negative reactance in series to negate it. So that's why I'm choosing a series capacitor to create a negative reactance that offsets this guy. Also, thanks for pointing out the chat. If I'm looking at my my notes over here, I won't see chat popping up. So we'll kind of do a parallel case in a moment. Just keep that in the back of your mind. So we'll go back here. So from a visual perspective on the Smith chart, if I have a matched real part, but a mismatched reactance, I will fall somewhere on this circle right here. So I wrote a little thing here that's going to highlight that, right? So I'm just going to copy and paste that. So you notice I'm just going to plot a circle. It goes from 0 to 2 pi, and I'm going to center it at 1/2 with a radius of 1/2. And then we're going to do a little polar plot of that circle. Let's come back here. So I'm going to call it the magic circle. The book doesn't really give it a name, so I like the phrase magic circle here when we do this. So you notice all I did was highlight that blue circle. So that is the magic circle that we care about. If we're anywhere on this circle, in order to create a match, all I have to do is insert the appropriate component in series, right? So if I was down here in a negative reactance, I would bring it up using a positive, which would be an inductor, Or if I'm up here on the positive side, I need a negative series reactance, which will be the capacitor there, like that. So a fun little exercise in your head now is, suppose, I'm going to just say XC is a bunch of values. I'm going to go from, say, negative 100 to plus 100, 100 ohms with 1,001 samples. I'm just going to say my input impedance is going to be my load plus J times this series. I'm going to call this S actually for series, right? So I could either put an inductor or a capacitor, and that will manifest as a positive or negative reactance. And now I'm going to calculate my gamma, I guess a gamma S for the series here, okay? And I'm going to, it's going to be Zn minus Z naught divided by Zn plus Z naught. And now we'll just plot that and you can see what will happen. So gamma S, gamma, and let's give this, what color should we do? Let's do red, okay? Like that. There you go. So you see what happened is if I added reactance, it followed along this circle in this direction. And as I go to infinity, it'll want to go all the way to the open circuit, right? And as I put in the negative reactance, it followed the arc this way. Then eventually just kind of becomes negative and it'll want to go around that circle. So this is a key point, is if I'm on this circle, I just have to add a series reactance to get the appropriate value here. So in particular, let's just do from negative 75 to plus 75, because that's the actual value. And I see as I go to negative 75, it brings me to the center of the Smith chart, which is exactly where I would want to be. So that is kind of the first step in lumped element matching, how it shows this connection to the Smith chart. There's this nice, simple visual pattern in the Smith chart that these curves are going to follow as you imagine this series capacitor. There's a knob where I can dial the reactance, positive or negative, and there'll be some appropriate capacitor or inductor associated with that. And as I twist that knob, this little dot is just going to sort of follow this arc here. So that's one of the first key ideas we need to get very comfortable with, is following the arcs. So the next question is, what about parallel? So let's do this same sort of example, but I'm going to put in a parallel reactance here. So this is the part where it gets a little tricky. So what I want to do, let's create a load reactance. I'm going to say YL is 1 over Z naught, and I'll just say plus 0.1 J, okay? Load reactance. So this has units of mhos, or you can say Siemens, I think is the unit for that. So similar little exercise. So now I'm going to just do the following. So you notice we're not working in an impedance land, we're doing a reactance. And just suppose hypothetically the real part of my reactance is matched, but not the imaginary. So I'm going to calculate the equivalent load impedance. So I'm going to say ZL is 1 over that. So let's remove this. Okay, so you see what I just did here is, in fact, we'll not even worry about this stuff now. I'll just keep it clean. So instead of an impedance where the real part was matched, I have a reactance where incidentally the real part is matched, but not the imaginary. So then we will calculate, so that's the equivalent load impedance now is 1 over that, and we'll follow the chart here. So let's ignore this stuff. So now you'll notice I'm over here somewhere, and this is where things get a little interesting, and that is, in fact, that's actually kind of a high reactance. Let's put like 0.01, well, 0.05 maybe. See how it likes that. There you go, that's a little better. So now what I'm going to do, I'm going to plot the opposite circle here in red. There we go. So this is the interesting thing, about Smith charts that the book did not emphasize, and that is anything you can do in the impedance perspective, you can also do with admittance. All you have to do is flip-flop your axes here, your coordinates. So that same circle here, where it was a real part of 1 for my impedance, everything will behave the same. It's just on the left side of the Smith chart. And I think you also have to flip the top and the bottom here, right? Because you can see how a positive susceptance here. So this had a positive value here. It went into the negative plane here when I went to impedance, okay? So that's an important little point here. Okay, but now the rules are going to be the same. Anything I do in parallel is going to follow this same circle. So before it was series impedances, series reactances, and it was following this blue circle. Now I'm going to do parallel, and the same fun little rules are going to apply. So let's go back to the overhead here. So in this scenario, it will look something like this. Here is some load, only instead of expressing it as an impedance, I'm going to express it as a reactance. Okay, and instead of adding something in series, I just add something in parallel. So I'm going to call this, say, YP or something. The book says JB instead. So in fact, yeah, we'll leave it that because we don't want any real values to this guy. So the equivalent admittance looking into here, we would say YN is just my load plus JB. Incidentally, I forgot what the word for this was when I was recording the lectures, and I looked it up later. It's called susceptance. Okay, so that's resistance when you're impedance, and then it's reactance, and then you have conductance and susceptance when you do the opposite of everything. So this will be some, so this is where it gets a little annoying because I don't think there's a dedicated letter for this here. I think, oh, it's G, that's right. So you'd say GL plus JBL plus JB. There we go. So this is the load here, the load conductance, load susceptance, and then this is the susceptance of this little parallel guy that I'm going to add. So this is why impedance and admittance are going to follow the same rules in a sense, just whatever I'm doing in parallel, we have this same rule applying here. So what I want to do is I want my JB to equal negative JBL. So whatever I put here, I want it to negate the imaginary component of this so that I get a match. Because we've assumed that GL is actually 1 over Z naught, right? So it's there's a characteristic admittance looking into here, and the real part has been matched. So the similar idea is now going to happen. So let's go back here. So we followed along that arc. So let's do the same idea. Instead of calling this x sub x, I'm gonna call this BP, or just B. So this is the variable susceptance here, okay? So I'm again gonna do a length space. I'll do from like -1 to 1. Pretty small values tend to work pretty well.
You're not sharing your screen.
Oh, dang it, sorry, thank you. Okay, so I'm just gonna do that same thing where I'm gonna twist the knob and we'll see what happens. So we'll say Z, oh, how do you want to do it? So yeah, we'll say my Zn is going to be the parallel combination of JB plus 1 over ZL, like that. That kind of makes sense what we're doing there. So this is the parallel combination of my load impedance plus that reactance there. So my load and that parallel reactance. Since it's already a reactance, I don't have to do the 1 over there. And in fact, I don't have to do this here. I can just say YL. Or yeah, and so Zn now, we're going to calculate. So the gamma, I'm going to call this, say, gamma P for parallel. And here's what you'll see. Whoops. Oh, sorry, I got to do a dot divide. Here we go. Oh, and I got to give it a different color here. Let's call this green. Oh, that was a huge range. So let's maybe go 0.1 to 1 like that. There we go. Okay. So you see that that little magic. So this is where we originally were, and by adding or subtracting some of that susceptance there in parallel, I moved along this circle here. So you see, if I overdo it, I can overshoot the center of the Smith chart. And if I go the opposite direction, it'll want to take me around to here. So this little piece of visualization is just very, very important because it's going to occur again when we do the series stub matching. You know, this similar notion where these are the magic circles that I want to land onto. And all I have to do is either add an appropriate series reactance or parallel to get where I want to be. So now, hopefully that kind of made, are there any questions at all about this? Because it's very important to just see that little visualization there when we go through these problems. Okay, so just remember, when I'm dealing purely with series impedance, I will be following this circle here. And when it's reactance or putting things in parallel, then this circle over here is what I'm going to care about. All right. So let's now make things a little bit more complicated. So instead of dealing with reactance, let's go back to impedance. And now we're going to mismatch the real part, plus 75J, okay? So we'll go through, we're just going to run everything again. I'm just going to kind of delete this stuff. Okay, so I still have my two magic circles here. Here is now, I'm not on the circle though. So I do know that if I can somehow get this dot somewhere on this circle, then I just need to add a series impedance to bring me down to a match, right? So the question now is, what do I do to get this dot either somewhere on this blue circle here? Or equivalently, could I get it onto the red circle, right? So this is where you have to make that decision between the high-low or the low-high network. So the first, let's go back here. Stop sharing. So let me forget to share again when we go back. So now we're doing this situation again. So here's my ZL, which is RL plus JXL. So for that, those first couple exercises, we were assuming the real part matched. Now we've removed that and we saw we were not on that circle. But I do know that if I do something here that causes the real part to be matched, I just have to add a series component somehow. So the rule is, for this situation, we fell inside that circle over there. So let's just hypothetically add a JB to this, okay? So we're in this situation. This guy isn't matching, so I'm going to add this. So the question now is, what is my input impedance, seeing looking into here? You know that Zin is going to be 1 over JB plus 1 over ZL, like that. So I'm going to pretend this is a knob that gets dialed again, okay? So let's go back and share. So let's say B is in space, negative 0.1 to plus 0.1, do another 1,000 samples. Now my input, so I'm imagining this is some parallel susceptance here, okay? So it's gonna be 1 over J times B plus 1 over ZL. And in fact, I can just say YL to make things a little easier. Just say YL is 1 over ZL, like that. So you notice my input impedance will just be 1 over that. So now my gamma, I'm just going to calculate the reflection coefficient over all these little values. Zn minus Z naught over Zn plus Z naught. And then we'll again plot the real and the imaginaries here. So I'll just say gamma in, and we'll just do a little, maybe do a blue line, or I got red and blue already. So let's do this. I'm going to make my magic circles. They're both going to be blue. And then red will be the little arc that I'm following here, like that. There we go. Okay. So you see what just happened here. I just hypothetically added some parallel susceptance, and I pretended it was a knob that I could dial to plus or minus values. So you notice by putting a susceptance in parallel, which hypothetically could just be a capacitor or an inductor, I follow along these same admittance circles here. So this was the admittance circle when the real part was matched, and these are just admittance circles now when They're sort of off matched. So you can see all I have to do is pick an appropriate value where I either land here and intersect with the circle up here, or I could swing the other way and land a value down here. So that's why there are two solutions when you go through the algebra. So I have two options. I can dial it up to about there, or I can dial it back down to over here somewhere, okay? And then you'll notice once I dial to one of these points, I just have to add the appropriate series value here. So let's stop sharing again. We'll go back to here. So the end result looks like the following. I have some series value here, and then I have the shunt is the technical word for it, and we're like so, okay? So there's my Z sub L, there's my JB and JX. So the idea is this little block here will follow the circles on the left, right? So if we draw a quick Smith chart here. So by adjusting this knob here, I had some starting points and it took me along these arcs over here. And then I had the magic circle over here, like so. So I adjust this knob first. I can go up or down. It will either take me to this intersection point or that intersection point. And then as we just found out, once I'm on this circle, all I need is an equivalent series, which will then take me either that direction or that direction. So that's why I say in your mind, you have all this math that the book does, right? So you follow along with the derivation and you get these analytic solutions. And they're pretty nasty. Like I went about halfway through this derivation before I said, you know what, screw it, I am not going to finish this. It's not super hard, but it's very tedious because you have to do all this mixing and matching of terms. And you match the real and the imaginary bits, and you calculate your B and your X, and you get this gigantic, nasty monster of square roots on top of square roots to calculate your B, which you then use to calculate your X. Okay, and that is the solution for the shunt case, right? And then they do it again for the series, right? And it looks like it's a very short little derivation to go from here over to here. But if you actually do this by hand, it's like a page and a half of gobbledygook, right? So this is why I say there's this distinction in your mind where I can just plug this straight into MATLAB and get a result. MATLAB will be more than happy to grind on these equations here and give me a solution. But you can see also there's this certain intuitive power in visualizing all of that in terms of just motion along these circles. Okay, so by adding the shunt reactance here, I go along these circles on the left, and then when I add the series over here, I just follow these circles on the right. So this also gives us one of our first design rules, and that is if my load impedance is inside this green circle, I have to use this configuration, because the opposite configuration will follow opposite rules like this. So this I like to call high-low. This is called a low-high network. But you'll notice the problem is if I try and do series first, I will only be able to follow along these circles, the black circle there. And it won't be able to land me on either of the magic circles over here. So this is why if you fall inside this green circle here, you have to do this combination here, the high-low. Because the low one will follow along these big giant arcs and get me onto the circle. Whereas if I do series first, all I do is twirl around inside and I can't break out of it. That's also true for the opposite case. If I happen to land over here inside the opposite circle, then I have to use this configuration here for the same reason, because this series value will follow me along these big giant circles here, whereas this one here will just sort of twirl me around inside here. And then if you're outside, then I believe it doesn't matter which one you use. You'll have a solution either way. So the books kind of gives this little design rule where it says if RL falls within this circle here, so that is greater than Z naught, then you need to use this configuration. Otherwise, just use that one. I think that's the rule they say. Or I might have that backwards, actually. Yeah, if I'm greater than Z naught, sorry, I have to use this configuration because that would put me over here. So this would be greater than Z naught, and then RL is less than Z naught would be this one over here. So that's where you get, this is called series shunt, shunt series, or as I like to say, low high, and this is high low. I think that is a term I think I learned from taking antenna theory or something. It was Dr. Gandhi was the guy who introduced that term. But I don't think this book uses that terminology, but I kind of like it. It's very straightforward. So how much time? Oh, good. We've got a little bit of time left. So now, any other questions here? I'm going to do some motion around. Now's a good chance to kind of chime in with a question. But again, there's this disconnect between the mathematics and then this nice visualization of what's happening in the Smith chart.
Sorry, Professor, could you show on your figure there, the Smith chart, where we are implementing high, low, and low, high again? I apologize. Yes.
So this is, so going from left to right, this one here is a high, low. Okay. And we can do the opposite scenario as well, and you'll see it follow the other circles. So just remember the shunt next to the load, this is the high low. So the low is right up there next to the load. I'm dialing around my B and it takes me along this red arc. And so the idea is I dial up and I get to here, and then my series, the high, will take me along the blue circle. So we'll do a little bit of more reinforcement of that in a second. So I created a script. Here we go, L section matching network. I kind of wrote this a while back. So you notice you have so here's my load. I did this nice little ASCII art here. So that's low, high, and this is high, low. Or you can say shunt series and series shunt. And you notice all I did was just plug in the equations from Posar on page 230. So I'm kind of have mixed feelings because I feel like part of your understanding is, can you write a function that implements this yourself? Because the idea is I want to give you a characteristic impedance and a load, then you have to return the reactances and the conductances that will give me the match. So you notice if it's a high-low network, which is defined by RL greater than Z naught, then it follows these equations here. So this is equations 5.3 A and B from Posar, so page 230. And if you're doing the low-high, you have to use these other equations over here. So that's equations 5.6 A and B. So let's make a little note here. EQ 5.6 A and 5.6 B. And then up here, this was a 5.3. Okay, so if you've got your book out, you can see what's happening here. So I'm just going to do a little copy and paste. And we are not doing that. There's a practice problem. Okay, sorry, that's all written. Okay, so pretend that didn't exist. So now we're going to calculate the analytic solution. Going like that. So this is the function I wrote, where all it's doing is solving those equations in Posar. Right? And I went through the derivation in the lecture. As you saw, the derivation is a little tedious, but it does have a nice, straightforward algebraic solution. It's just a mess of gobbledygook of quadratic expression, right? So what we're going to do, we'll run that, and we'll get a reactance and a susceptance, right? So you look at here, it returns two values, because remember there are two solutions here that will get this to work. So we get, let's see, so right now we're in the low-high, so trying not to confuse these networks here. So B is the susceptance, so you notice there's a positive and a negative value here. And then there's an X that will take me along the curve there. So the B's correspond to either going up or down the circle, and then the X will correspond to coming across this arc here. So a neat way to visualize that is we'll do that Lin space thing again. So I'm going to kind of take this stuff over here. And instead of just putting in arbitrary values, I'm going to put in, oh, let's see, I got to give this a different name here. So call this B shunt or something like that. So I have this vector of two solutions here. So I'm going to say B of 1 to B of 2, except this one's the negative, this one's the positive. Okay, so there's going to be two solutions in there. And then I'm going to just call that B shunt like that. There we go. So this is what happens when you calculate the result analytically, and you see how the arc will take you right up there and it touches the circle, or you go the other direction and it takes you down the other way, like that. And then now I have an X, so I'm going to call this just X series, I guess. This will be X of 2. Oh, except you got to be a little careful. So we're going to have to do two arcs now. So I'm going to go 0 to X of 1, like that. So I'll just call that X1. And then there'll be an X2, like that. And this one's negative, so actually I have to go from X2 to 0, like that. And again, we're going to calculate a new input impedance. Okay, so what we have here, this is with the shunt added, but now I'm going to add the series impedance here. So it's just going to be Zn plus times X1, like that. So we got to be a little careful here, because this is an array now. So I gotta, so let's do this. I'm gonna say Zn1, just gonna be B of 1, like that. Zn2. So this is going to correspond to just the tips here at these little endpoints, rather than drawing the whole arc as we go through that, right? So we'll say Z sub, we'll call this high-low. That's what we're doing right now. Zn1, well, that's getting a little confusing. Let's just give it a name. Z1 is Zn1 plus, there we go, something like that. Then this will be Zn2 plus that. So now I have to calculate a bunch of reflection coefficients. So the idea, just to review, we've pretending now we've either followed the arc up to this point or that point. I just want to draw an arc along this guy here. So I'm pretending my X is a knob that's going from like 0 to the matched value there. So you're going to see it fill the arc from here to here, or it's going to go from there to there. So I'm going to say gamma 1 will be Z1, like that. Gamma 2. So let's try this guy here, gamma 1. So assuming I didn't make any silly mistakes, we should see an arc like that. There you go. So you see what I've done. So sorry, that was a lot of little steps. All I'm trying to do though is just play connect the dots, right? So this was my original load impedance here, and I just sort of drew two arcs as imagining you twist the knob of that parallel shunt there, that B term. So the first term took me down to here, and then I just played connect the dots from there to there, okay? So that was this idea. I just created an array of 1,000 samples, which took me along this arc all the way up to the match. And then again, we can do gamma 2. Let's give this a different color, magenta. And you see how it goes the other way, like that. Okay, so that is how lumped element matching works. And again, if we did be low-high, the same things would happen. Just instead of thinking about it in terms of impedance, you have to think about it in terms of admittance. And all of that magic will be flipped over onto the left side of the Smith chart. And so you'd follow an arc up to here and then back down to center again. Okay, so I think that just barely finishes us. We couldn't do the frequency response, so that's okay. This was the most important thing I wanted to really connect is there are the algebraic expressions, which you can just solve, but they don't have that visual intuition of like, no, I'm following these little arcs to go from some starting point here to end up at the center of the Smith chart. Okay, so any questions on that? That was a lot to digest. I'm going to give you some homework assignments that kind of have you retrace some of these steps. And I'll kind of upload this script file later so you can play with it when you do your homework, okay?
when we were working in the low high, are we still working in admittance, or have we switched over to impedance?
You're technically doing both. The shunt is the one that will follow along this red arc here, these circles, and then series will take me along these other circles. I guess, how do you name? Can we give them a name? Just an admittance circle will be touching the left of the Smith chart, and then a reactance circle will be over, or an impedance circle, I guess, would be over here on the right side, touching the right end of the Smith chart. So you're kind of doing both, right? Because you have a series and a parallel element in this matching network. So the key is the shunt. When you twist that knob, it takes you along the admittance circle, and then the series will take you along a reactance circle. I hope that helped. It'll take a little while to sink in. So that's why I'm going to do a practice problem in the homework where you kind of have to code this yourself and watch what happens.
And you said the book does not call it high-low or low-high. They call it a shunt, rather?
Yeah, it says, they call them L sections, which is kind of explanatory, but there's the, what do we call it? Where is it here? Do they even give it a name? They just say lumped elements. Yeah, they don't even quite give them names. Analytic solutions. Yeah, they don't even really give it a name. So somewhere I heard the term low high and high low. I think that's when I took like, it might have been an antenna engineering class at the U is where I first heard the words low high and high low. But that just corresponds to, here, let's look at the camera. So you can see high, low, low, high. So I think that's a nice handy naming convention for this, because I'm sure that's out there in some other contexts as well. Just the book doesn't seem to call it that.
So in the example that you have on your MATLAB on your screen, to go up, the shunt will move up and down, and it's our choice if we want to go up or down to get to the real circle and then get to one.
That is correct. There are two perfectly valid solutions when you do this. And the correct one is whichever one makes you happier, I guess. Sometimes you might prefer maybe the values of the capacitors are easier to get or not. That's actually a good point that you bring up is there are technically two solutions to this. In practice, however, the book it makes a good point that you generally wouldn't do this for like super high frequency stuff. Like this lumped element matching is really only viable for frequencies below a gigahertz or so. When you start getting really, really high, you have to use more like the stub matching. So we'll talk about that Monday, but this is actually a great stepping stone into that, right? So this is kind of a straightforward idea because it has nice foundation in circuit theory. And the same ideas are going to apply when we do stub matching, which is a little bit more practical at higher frequencies. Just the circles will be a little different, but I like this because it's a nice intuitive foundation to start thinking about these things in terms of the Smith chart. But yes, there are two solutions. They're both equally valid if you can find the right components for it. Sorry, what was the question? Yeah.
The follow-on to that is like, why is the stub now being used? Because we're using a stub to put an effective capacitance or inductance on the transmission line versus just slapping an inductor on it. So I guess when we get to the stubs, we'll discuss why the stubs outperform. Okay.
Well, because like it's very easy to just machine in a length of transmission line on a little printed circuit board or something, right? And that thing will still work very well upwards of 2 to 3 gigahertz if you do nice thin little traces, right? But when you're doing 2 gigahertz, capacitors and inductors really don't act like capacitors and inductors anymore. All the parasitics buried inside the device start really causing issues. So I thought that was a good point. That is a good point the book says, is this lumped element idea is probably best only used for lower frequency stuff below a gigahertz. When you get higher and higher, you wouldn't use a lumped inductor anymore. You would use the little stubs. But the actual physics of what the stub matching is doing is it's behaving like equivalent series and parallel networks. So that's kind of cool. they have an you can think of them as an equivalent capacitance or inductance anyway. Anyway, so that was kind of a lot to digest. So I appreciate you hanging in there. I remember a lot of this was not explicitly made clear to me when I went through this the first time. They just sort of baptize you by fire in a lot of classes. But having been through that, I know that there's certain gaps in the transmission line stuff where the book sort of casually mentions offhand that there's this notion of the admittance chart, but it doesn't really explain what the rules are in terms of, how would I move along these circles here? So that's why I think this is a very powerful visualization. So all the rules we just did with the high-low, they will do the exact same thing with the low-high, just instead of carrying out these little arcs over here, they'll land on this circle and come the other way. So again, I'll think of some nice homework problems that have you do that yourselves and visualize those little transitions. All right. Any other questions?
When we did, I'm sorry, I recall similar kind of exercise when we were doing, what is it? I think we were determining the length of the quarter wave transformer, moving away from the generator, moving toward the generator, these kind of exercises. But instead, in this exercise, we're adding an element to, we're adding an actual passive element to the line without changing the length of the line, correct?
Correct. Yep. That's why it's called lumped element. You're physically soldering a capacitor or inductor, ceramic chip or something onto some microstrip board, say. Dr. First, when she did 3300, I think she has a great picture of an actual microstrip board with some components on it. But she's doing stub matching, but you can imagine, I guess, here, let me do a little visual. I'm gonna actually stop recording because we're kind of past time, so you guys can go ahead and leave if you want.